First, I thank the organizer for offering me the chance to represent my latest work with Olaf Reimann. It's called the T-RAX, Transversely Resonant Axion experiment. This is mainly about the concept, so I think my talk will be rather short. So by now, I don't think I have to convince you that the axion is a good dark matter candidate. The problem with the detection, however, is that the axion mass range can span in a multitude of the magnitude, and that makes the experiment hard, but also there are many experiments looking for the different energy ranges. But however, I want to point out that not all the mass ranges are equally motivated, and especially if we assume that the path-sequence symmetry was broken after the cosmic inflation, so-called the post-inflationary scenario. In such case, we don't really have to worry about the specific theta angle, initial theta angle. We only have to care about the averaging. And the latest simulation prefer this energy range between the 40 and 100 microelectron-volt. So that's the preferred range for the post-inflationary scenario. Now, if we put it in the usual axion mass versus photon coupling plot, this red band is the mass range I just mentioned, post-inflationary simulation done by Bushman and et al. So the cross area between this red band and yellow band, the QCD-axion, is the most favored region to look for. However, we know that this area is left mostly untouched except from a few limits from the organ. Mainly because, as Stefan and then Benjamin already discussed in detail, the cavity resonators becomes much less sensitive in this higher frequency or the higher mass region. So we have to come up with some different scheme. And T-RAX want to solve this problem in some different way. So in the first half of my talk, I will discuss the principle of the T-RAX, and then second part, I will discuss the simulation result and then the consideration of how to actually implement it in a realistic setup. So first, we begin with the usual Prima-Coupling interaction. We begin with the axion field A oscillating on top and bottom with the axion mass or the axion frequency omega A. And we still assume that the axion wavelength in this mass range is a lot larger than your typical experiment. So axion field is in phase throughout your experiment. Now, this couples with the external magnetic field, BE, and create what we call the axion-induced electric field that's also oscillating with omega A. Now, you want to detect it, but then, of course, this field is extremely tiny, and we need a way to amplify this signal. And the typical solution is to bring into a cavity. Here, I put the simplest cavity that consists of two mirrors. If the fundamental mode of this simple cavity matches that with the frequency of the axion, then the axion will excite the fundamental mode, and you can get the resonance booster of the signal. However, this doesn't have to be two mirrors. You can actually excite the signal from a single mirror. That's the idea behind the dish antenna experiment. The axion-induced electric field will excite the traveling wave from a surface of from a conducting surface, such as a metallic mirror, and you can directly detect it using a traveling wave detector, such as an antenna or the waveguide. And the beauty of this dish antenna experiment is that there is no fundamental limit to scale up your signal power. You simply have to increase the area of your mirror to increase the signal power. Another additional benefit for the traveling wave detection that people don't usually discuss, but I want to emphasize, is that the traveling wave detection components, such as the horn antenna or the waveguide, are well developed, and they are more suitable for detection at the higher frequency. They just become less reflective and then less lossy than their counterpart to detect the standing wave, such as a dipole antenna or the coax cable. So this is more favored experimentally. So, but of course, the problem is there a way we can increase the signal? And I just mentioned that you can increase area, but then you also have to put it in a bigger magnet, more powerful magnet, which is very costly. So the alternative idea is to replace one of the mirror of the cavity with a dielectric, or bring additional dielectric that reflect the signal with the reflectivity gamma, and it create the resonance. And you can increase the standing wave stored inside and the leaking out power from it, and you can detect it. That's the idea behind the director Halescope, and then you can. This is the simplest direct Halescope, and this is a way to increase the signal. However, this signal power is still too small, and especially this is limited by the magnitude of the reflectivity gamma. Usually, this is already set by the material you choose for the dielectric, for example, 10 for the sapphire, and so on. So there is no really easy way to increase it artificially, unless you bring more of them, like in the case of the dielectric heloscope. But then it comes with a practical issue, such as a more complicated system and how to align it, and then long optical wave axis, which forces you to use a dipole magnet. So the question is there a way we can increase the gamma even further without making the system too complicated? The solution I propose is to bring a sidewalls and create a waveguide. The idea is that when your frequency, resonant frequency is very close to the cutoff frequency of this waveguide, then the reflectivity gamma can increase almost indefinitely. Okay, to give you more detail, the reflectivity is decided by the ratio of the traveling wave impedance between this empty section and the section filled with the dielectric heloscope. And from your E&M book, and this traveling wave impedance for the TE mode is inversely proportional to the 1/beta, the propagation constant. So the data becomes 0 as you approach the cutoff frequency. So here is the plot I brought for our example geometry. The benchmark frequency is 19 gigahertz. And if you consider the impedance of the empty section for the 8 millimeter waveguide, this is the cutoff frequency, and this diverges to the infinity as you approach the cutoff frequency. However, on the other hand, the impedance of the sapphire field section here remains more or less set as constant at 100 ohm, and the cutoff frequency for this section is actually way below. So there you can achieve the sharp contrast of the traveling wave impedance and the large reflectivity near the cutoff frequency. So this is the idea behind the T-RAX, which stands for the Transverse Resonant Axion experiment, and transverse resonance here means there is also additional resonance between here when you think about the system as when you consider this waveguide as the emitter of the additional traveling wave. Now, you can further increase the signal power by adding more such cells. So you basically create a coupled oscillator with a distance between the mirror and each cell, roughly half of the guided wavelength. This will change if you consider the finite thickness of the dielectric, but I will discuss that's more technical detail. And then to find the axion mode or the frequency, the exact spacing that can boost the signal at your frequency of interest, you calculate the phase evolution of this traveling wave being reflected, and that I call the dispersion relationship. And another practical beauty of the system is that you can collect all the signal from multiple cells into a single port. And so this is a monolithic, what I call the monolithic readout, and this mode can maximize the signal to noise ratio and then simplify the readout scheme. So that was the principle. The second half of my talk will be about the simulation. So with the principle, here is some more realistic geometry for the simulation. The left half of the geometry is the cell itself I just described. The right half is a taper which collects the axions, induce the signal power into the standard waveguide. Now the booster section or the axion power conversion section consists of 2 cells in this simple geometry. That's divided by the 2 dielectrics, and I use a sapphire in this case. The external magnetic field shown here is going through the system vertically, and then with the geometry I simulate 2 parameters. First is reflectivity. So imagine you put your network analyzer at the waveguide, and you measure how much of the signal you sent is reflected, and then you can compare that with your measurement. And the second is the axion-induced power, what I just described in the principle. If your axion can excite this resonance mode here, then how much of the signal actually comes out. Now, and this is the simulation result in the frequency versus the first is the first x-axis is the magnitude of the return, S11 or the reflectivity, and you can see the 3 dips. The first corresponds to the taper mode, which is just a mode crossing inside the taper. This middle peak corresponds to the axion mode, but this are the 2 cells are antisymmetric, so there is a minimal power from the axion in this signal. The third peak is what we call the axion mode. Then the 2 cells oscillate in resonance. And in our case, at the benchmark surface conductivity, we expect the power boost about 80,000 compared to the case for the with a single mirror alone. And of course, if we can reduce the resistivity of the surface or increase the conductivity, we can boost up the signal. Here in the little optimistic case, when we lay the internal wall with a high temperature superconductor, then we can increase the signal power by more than factor 2. And this is the figure of the axion mode, the resonance mode I just described. Figure A is the basically mode crossing inside the taper. So this is a parasitic mode. B is when the 2 cells are resonating but out of phase. And the C is when they are moving and resonating in phase. Now, the system should be able to also scan mass range. So with the tuning and the different mass range, I propose to move the dielectrics. And as I just mentioned, that the distance between the mirror and the dielectric is roughly the half of the guided wavelength, or 1/2 of this inversely proportional to the propagation constant. So we can move the dielectric, for example, by moving having the rod moving across the slits on the top and bottom. And in this example geometry, I moved the dielectric position by 40 millimeter, and that can change, with the 2 millimeter steps, and they can change the frequency tuning about 2.5%. And the required precision for such motion is 50 micrometers. So this is already achievable with the current technology, for example, cryogenic stepper motor. And we have to want to put the detector inside some real solenoid magnet. So for this, we want to minimize the footprint of the system. And the problem is this long taper. My solution is that we can fold the taper in half by using, like, for example, 180 degree band waveguide, which sounds radical, but if you actually look at the specs for the commercial waveguide for this part, they actually reflect pretty little. The return loss is about 40 dB, as long as you are far above the cutoff frequency. So you have to need some section to increase this waveguide width, but then after that, you don't have to worry too much about this reflection at the band. And then if you minimize the geometry, then you can put it inside the commercial solenoid magnets that can easily provide a 10 Tesla magnet, or I hope to put it in in the strong proposed 30 Tesla magnet, which can still fit in. So here is a projected sensitivity for the benchmark setup I just described. Here I assume the 19 gigahertz single quantum limit, and the wall is laid with the copper and operating inside the liquid helium temperature. The sensitivity for such setup is this a solid line, and this already begin to touch the large QCD-axion range. And if we put the system to the limit, like for example, if you build a 50 centimeter tall system inside the 30 Tesla, then we can even dig into the KSPZ line and the lowest frequency. To go even further, then we have to come up with some different readout schemes, such as a single-photon counter, and this is getting really common. This is becoming real, and this is an example list of all the major Axion experiments with their readout system. Now the heterodyne system is more advantageous above, say, 50 gigahertz, but this boundary is pushing lower, and this is moving really fast. So this is really optimistic. I want to just point out that because T-RAX can funnel all the sort of signal power into the single port, this can maximize the signal to noise ratio, and this will be the ideal platform to apply the single photon counter that can really lift our sensitivity to the QCD-axion range. So here is my summary. I propose a new detector concept that's tunable and can fit inside a solenoid magnet and has some modest sensitivity to the QCD-axion lines in the post-inflationary scenario. Thank you very much. We just machined our prototype T-RAX in the workshop at the Max Planck Institute, and here's the picture of the copper, one half of the cavity. And this we also cut the sapphire to fit it inside, and I just did the first measurement, reflectivity measurement last week. So I will share the result in the hopefully next Patras. Thank you very much. And yeah. I hope you had a nice dinner last night.
Yeah, thank you very much, Chang. I'm sure there are questions from the audience. Yeah, in the back.
How does the axion transfer momentum to the electromagnetic wave? In other words, what do you have to do to make sure that you have phase matching?
Can you repeat the question, please?
How does the axion transfer momentum into the traveling electromagnetic wave? In other words, what do you need to do to ensure phase matching between the axion and the
You're asking for the very first slides, or?
Well, in your entire concept, you have a traveling wave, and so you started off with nothing, and so how does the axion
Well, first we
momentum?
assume that, well, okay, well, this will be more question for the theorists, but first we assume that the axion phase is more or less in phase still in our setup, because the debris wavelength in our setup, in our frequency range is still like 5 or 10 meters, so our system is very much smaller. And the wavelength of the signal system is on the order of a couple centimeters. So we have to machine the system. We need a mechanical tolerance much smaller than the 1 or 2 centimeter wavelength. But this is feasible. I mean, people are already doing it. So, yeah, traveling waves will be mostly in phase.
Okay, we have time for one more. Yes? Maybe I can.
So in your projected limits, it looks like you have a very wide tuning range for your system. Is that?
No, this is not achievable with a single system. You need a multiple.
Okay, so you have like different versions of T-RAX.
No. No, if I put all the actual system, this will be too crowded and then not really feasible. So no, we certainly need many different arrays for the different frequencies.
Okay, thank you.
All right. Then let's thank Chang again, and we can move on.